Okay, great. So we have our first contributed talk of the conference from Alexander Zlokapa from MIT and Google. And just a reminder, contributed talks are like 20 minutes with a few minutes for questions. So, and he'll talk about Hamiltonian simulation for low energy states with optimal time dependence. So looking forward.
Thank you. Yes, I'm Alexander. I'm co-advised by Aaron, who you just heard from, and Ike. This is work I did while I was also a student researcher at Google. Okay. So the nice thing about coming to QSIM is that I don't have to motivate Hamiltonian simulation. I don't have to tell you the Feynman quote, but I will define what I mean by Hamiltonian simulation anyway. Just to make it a bit formal, the model I'm considering about, I should mention also on the title slide, this is joint work with Rolando Soma. Okay, the model of Hamiltonian simulation I'm talking about is this kind of black box picture where we take in a state coherently, we're given a time, some scalar, and we have some oracle access to a Hamiltonian, which I'll say more formally soon. And up to some epsilon error, we want to produce the time-evolved state on some qubits. So largely speaking, it's good enough to think about the Hamiltonian in terms of the kind of standard block encoding form that many algorithms use. So if I want to time evolve a Hamiltonian H, I can always shift it by a constant, and that will only produce a global phase. So we can make a constant E. And then a block encoding rescales a possibly offset Hamiltonian by another constant, alpha. So that the shifted and rescaled Hamiltonian H prime, whose eigenvalues I'll call lambda H prime, can be written as a block matrix within a unitary T. And so the block encoding access model kind of assumes that you have efficient access to this projector in this unitary, so that you have a submatrix that is H prime. Now, more rigorously in the proofs, we actually consider the kind of two common ways to make these block encodings. No worries if you've never seen these before. They're not too important in understanding the talk. I'm just going to define them for completeness. The Hamiltonian can either be written as a sum of unitaries, where you have access to those unitaries and the coefficients given by what are normally called the select prepare oracles, or you can assume your Hamiltonian is sparse. These are two formal things that people use in order to try to model the query complexity to these oracles, since it's a good proxy for kind of the costs you would face actually doing a simulation of a Hamiltonian you might be concerned about in real world. So this is defining the Hamiltonian simulation problem. These are what I mean by H is provided by an oracle. So what is the Hamiltonian simulation problem formally? It's that you want to prepare a unitary and a projector such that when I look at the block matrix of that unitary that's like block encoded inside it, I have something that looks like a time evolution operator up to epsilon error. I'm just going to define it this way. You could define it in terms of trace distance or fidelity or something. But this is good enough for our purposes. And the kind of basic questions to ask are, how much does this cost in terms of number of queries to the oracles I wrote earlier? And how do we produce an algorithm that hopefully achieves that optimal cost? So this is all very fully general things, but I just want to make it all well-defined. So there's a good intuitive argument, actually, to see what the cost of the simulation is, the lower bound. And the intuition comes from just looking at the phase acquired by the highest energy state. It's going to be oscillating somehow as you time evolve the Hamiltonian. And in general, I'm ignoring the global phase, just write H prime as H over alpha. If you want to look at the phase and the phase acquired by the different eigenvalues in the Hamiltonian, you're going to get some sine as you oscillate. And the frequency of the sine wave sets kind of the T alpha scale of what any algorithm is going to have to realize. You can actually just and this is a common upper bound based on quantum signal processing and quantum signal singular value transform ideas. You can just brute force produce this polynomial, this oscillating phase, and you can make polynomial approximations in quantum algorithms. And so the degree of that polynomial is also roughly the number of queries you need. And that'll go for a sine wave with frequency T alpha, like T alpha plus log 1 over epsilon, if I want to get this polynomial up to epsilon error. This also tells you what the kind of lower bound you should expect is, where you would expect T alpha as your lower bound because you need to be able to produce this polynomial regardless of what you do. Rigorously, this comes from a technique called the polynomial method. Okay, so that's the kind of, this is just Hamiltonian simulation. This is all known stuff. What's special is now we're going to look at low energy states. Unfortunately, Feynman doesn't have a quote about low energy states, but they're fairly common. And that's about all the motivation I'm going to give. They appear in chemistry. They appear in quantum adiabatic computing. Oftentimes, if you have a low energy state, you want to time evolve it. So we'd like to know, can we use that information to maybe do better than the kind of generic Hamiltonian simulation that I just showed you? So why might you think you can do better? Well, let's take our Hamiltonian. Its ground state energy, let's say, is E naught. If we could make the ground state energy look something like 0, so we just offset the Hamiltonian, that's fine, that's a global phase. Our phase only oscillates like T delta if the energy is at most delta away from the ground state. And so maybe earlier we had T alpha plus log 1 over epsilon, maybe now we can get like T delta plus log 1 over epsilon. The kind of standard theorems that tell you how costly Hamiltonian simulation is, coming from these no fast forwarding theorems of Aharonov and others, where you look at parity and so forth, they don't have a low energy state, so they don't actually rule out this T delta scaling that you might naively expect. So the first result is a stronger no fast forwarding theorem, where we show that in the worst case for both of the oracle models I described, you always need T alpha queries. So that holds even if your low energy state is only supported on the ground and first excited states, where those have asymptotically smaller energy than the norm of the whole Hamiltonian. So if I have time, I'll tell you a bit about the proof at the end. But that's kind of the first theorem that we show, that this naive hope just falls flat. In the worst case, you're going to have to pay for the full norm of your Hamiltonian when doing simulation. OK, well, we could end there, but we won't. There are some papers that have previously in the literature looked at low energy simulation. And they look at it for specific types of Hamiltonians and find some kind of speed up better than T alpha for simulating those Hamiltonians. So what happened there? Well, we show that it turns out you can write all the kinds of problems that people have found advantages for in low energy simulation. All those Hamiltonians can be written in a form that we call gap amplifiable Hamiltonians. The intuition for a gap amplifiable Hamiltonian comes directly from its kind of decomposition into as a square of the matrix A. So the previous settings that people have considered actually have this property all the time, where you can efficiently compute the square root of your Hamiltonian. And so we can repeat the same kind of questions we have before for low energy simulation, but instead of oracle access to the Hamiltonian, ask about oracle access to A. So what sorts of things fall into gap amplifiable Hamiltonians? One example that's maybe the most physically relevant is a frustration-free Hamiltonian. These were the systems considered before in the work by Sainoglu and Soma, when they looked at product formulas and low energy simulation. These are also, but that's only a special case of gap amplifiable Hamiltonians. These are more general objects. You can write them in general as if I have h equals alpha a dagger a, as having low energy states that are at most energy delta. You can always block encode those into the form of a block encoding with a low energy subspace between -1 and -1 plus delta over alpha, and vice versa. So it goes in both directions with efficient mappings. In general, you can always get any Hamiltonian into this form, but you'll pay some overhead cost. So we're going to just measure the oracle axis to A and ignore that overhead cost as the previous works consider. Because as I said, like frustration for Hamiltonians, you can do this efficiently. So pictorially, this is what we have. We have a block encoding. Its eigenvalues are always between -1 and 1 because it's a unitary matrix inside a unitary matrix. The low energy subspace is now going to be between -1 and -1 plus delta over alpha. And we're interested in an asymptotic regime where delta is much smaller than alpha. So now we ask the kind of same question we asked before. What is a lower bound? What is an upper bound? We're trying to get time evolution of a state confined to that small, at most, energy delta subspace. And now we're going to measure complexity in terms of accesses to A. So now we get into the main results. And the upper bound is unfortunately a bit ugly, so I'm going to walk you through it. If you have a gap amplifiable Hamiltonian with lower energy subspace delta, then there's an optimization of a parameter you can do, where for any gamma, we can give you an algorithm that achieves epsilon close Hamiltonian simulation with this kind of query complexity. You can choose your gamma depending on your problem. So I chose it optimally for some scalings to get a better sense of how things work. The first regime is when you have T alpha much larger than T delta, much larger than log 1 over epsilon. This is the most relevant regime. So if you actually want to simulate a Hamiltonian, this is probably what you're going to be facing. The dynamics are kind of dominating the cost here. Your cost is linear in T. And it's not like your error is you're so sensitive to your error that your log 1 over epsilon term is blowing up. So the big O complexity of this is T square root of alpha delta. That's better than the T alpha of just like a worst case simulation algorithm. And the last regime is a bit boring. It's just when you care so much about your precision that your precision dominates your scaling. And the intermediate regime is a bit artificial. You get this square root T scaling. It's just because you chose some precision like asymptotically between your alpha and delta. So that's a little artificial to think about. So we're really only going to focus on the first regime, and that's where the interesting lower bounds and so forth will be. So what is our algorithm? Well, very briefly, the algorithm is quite simple. You have access to the free square root of your Hamiltonian. The square root of the Hamiltonian will have eigenvectors already pointing in the correct directions. So what you do is you prepare, like that sine wave we had earlier, you instead prepare a sine of alpha t times the eigenvalue squared, because the eigenvalues have been square rooted. And then you LCU those together, and that's about it. So the algorithm doesn't contain too many new ideas. Formally, you write it out in terms of this thing called spectral gap amplification that Selma and Boixot wrote about around 10 years ago, and then apply the kind of QSVT machinery that Gillian and so forth worked on. So the meat of what I have left to tell you is about the lower bounds to get the optimal time dependence part. So these are the lower bounds we report. They are in all three regimes. The last regime is already known from the previous literature. The first two regimes, we have lower bounds. I'm going to focus on the first regime, where we also show a gate complexity lower bound that shows it's also tight up to log factors. So what is the idea for how we prove this lower bound? In the query model first. We're able to prove, using the same kind of technique, a lower bound of T alpha for the worst case Hamiltonian that's not gap amplifiable, and a lower bound of T root alpha delta when you're in the gap amplifiable case. The idea for how this works comes from Grover. So if you're familiar with Grover search in the Hamiltonian simulation formulation, you can write down a Hamiltonian that looks like a sum between the uniform superposition, like ket S bra S, and the projector onto the ground state. And the nice thing about the uniform superposition in this Hamiltonian is that it's actually confined to a low energy subspace already. It's confined to a subspace that goes like 1 over root n if you're searching over n things. And so you're able to, out of the box, have a state already prepared that you can prepare efficiently in the low energy subspace. And here your Hamiltonian is in the linear combination of unitaries format already. So you might think that this is mostly done, and indeed it is mostly done in the kind of immediate sense of Grover's is most of what you need. But the time evolution to solve Grover is tied up with delta. So if you want to get t and delta to scale separately, you have to actually introduce many Grover problems. So we instead study parity OR and give an adversary method lower bound for computing the OR of many parities like I have k bins, each with n items in them, and I ask, is the OR of the first half of the bin? I take the parity of all of those. So it's a somewhat more contrived problem. But this allows you to use k and n to separate the scaling between t and delta and produce the lower bounds of t alpha and t root alpha delta. Where for the second one, you just make like a gap amplifiable version of the first one. So that's in the LCU model. In the sparse model, it becomes a bit more annoying to show how things work because the LCU form is not already sparse. So to make the general lower bound work out, we instead put the problem on a lattice, which uses the technique of Andrew Child's, where it's like a spatial quantum search. Or in the gap amplifiable case, to make the Hamiltonian also gap amplifiable, we have to instead consider a Hamiltonian on an expander graph, where the ground state tells you where the marked state is, and we use like random time evolutions to project onto that ground state. So, okay, that's a bit of a mouthful, but that hopefully gives you some intuition for where these query lower bounds come from. The gate lower bound also comes from some well-known construction at the bottom of it, which is the Feynman-Kitaev clock Hamiltonian. This is already a frustration-free Hamiltonian, and so this is already gap amplifiable for us. If you were to look at the continuous version of the Hamiltonian, where you're just hopping along a chain, your Hamiltonian just looks like p squared, where p is a momentum. So now the technical work goes into making a low energy state as your initial state, and then time evolve your low energy state. The idea for this comes from a paper by Stephen Jordan from quite a while back, where you take, or actually not too long ago, you take a wave packet that's a Gaussian wave packet with a momentum and a width tuned so that it lives in a low energy subspace. And then you time evolve it to go propagate to the right across your circuit. So what I've drawn here is a line which is what my Hamiltonian looks like in the clock Hamiltonian, where I have identities in the beginning, identities at the end. And the idea is that you have the circuit in the middle. And as you time evolve, this wave packet is going to propagate to the right. And it's going to compute the circuit. So at the end, when you measure, you compute the outcome of the circuit. Everything is tuned so that your low energy subspace is like 1 over g squared if I have a g gate circuit. And evolving for time, g squared will bring it to the right order g gates and thus compute my Hamiltonian. You can get from that construction a gate lower bound using the counting argument of a paper by Ha, Hastings, Katari, and Lowe, where if you just count the number of Boolean functions and circuits and say that, well, if you're to implement all the possible Boolean functions that you could with a G-gate circuit, you're going to need around G gates up to log factors. So all this together gives a lower bound of G in order to compute this time evolution. And that gives you that matches with T squared of alpha delta. Compared to if you just had T alpha, then you would have like an order of G squared upper bound. So there's the rough intuition for the gate lower bound. I won't say anything more about the other lower bounds. The second one is from the polynomial method. But I think it's like square root of T regime is not really a natural scaling. So the first lower bound is really the main takeaway. we now have the algorithm that's tight in the query setting, tied up to log factors in the gate setting. And then, yeah, in the worst case, you have lower bound saying that if your Hamiltonian doesn't have some special structure, you're going to pay like T alpha for it. So I'll end on some open questions. We didn't work out the optimal error dependence in our lower bound for the second regime. We're missing the log 1 or epsilon factor. But it's a square log, so it's not too bad. And we didn't work out in the sparsity model the optimal sparsity dependence. I have a hunch that's quite technical to work out, given how it's been worked out for the general Hamiltonian simulation case by Guanghao Lo. Other questions that we don't know the answers to that are maybe more interesting are we've presented a sufficient condition for a speed up in the low energy subspace, but it's not clear if there's a larger or separate class other than gap amplified Hamiltonians for which you can get better, faster simulation. We also gave one example of where a square root axis has been good and helpful. Maybe there are other settings, some that have been looked at before, like linear systems or ground state preparation. But it's a good thing to keep in mind that having like a free square root gives you quadratic speedups in some of these things. And then lastly, we only looked at a free square root. Maybe if you have a natural setting where you can get higher powers for free, then that would also be make space for larger speedups. But we don't know how natural those are. Yeah. Thank you.
So we have time for maybe one question for the coffee break. That one you can throw. But...
Thank you for a nice talk. Have you done any numerical experiment with your work, or on some easy model like Hubbard model or Heisenberg model?
We haven't done any numerics. We just left it at the asymptotic kinds of statements that we make over here. Yeah.
Okay, let's thank the speaker again.